Hi everyone, my name is Chen Wang. Today I'm presenting to you our recent work SwingBot, which is a system built for tackling swing-up manipulation by learning physical features from in-hand tactile exploration. Our goal is to enable a robot arm to swing up a pen with unseen physical features to a desired degree. The whole task is performed with an open-loop control policy, where the robot follows a fixed swing-up trajectory and decides when to loosen the parallel gripper to enable the swing and when to tighten the gripper to decelerate the object to stop at the desired pose. This act is only possible where the robot could self-explore the physical features of the object in hand before the swing-up and figure out the best policy to achieve the goal. It is relatively easier to design a policy to manipulate a single object, swinging up a known pen in our case. However, how to make the policy generalize to different objects, since objects with different physical properties result in different dynamics and control policies, it is crucial to learn the physical features of the object that can be used for adjusting the control policy. Human manipulators could use their tactile feedbacks and various kinds of exploration actions to estimate the physical features of the object in hand. These physical features include the surface friction, elasticity, hardness, weight, etc. At the same time, humans could easily fuse the information acquired from different exploration actions into a general understanding of the object, which will later benefit the in-hand manipulation. To allow robots also explore objects with tactile feedback, we use GelSight tactile sensor in this work. It provides rich contact information between the sensor and the object. The yellow arrows here indicate the force distribution, and the tactile signal can also provide pose information for the object, as is shown in the white ellipse. With the tactile sensing, SwingBot conducts several tactile exploration actions and fuse the information into a combined physical representation of the object. Based on this representation and a forwarding model, the robot could find the best policy to complete the swing-up task. Prior works mostly focused on using data-driven vision techniques to estimate the physical feature of the object by looking at their appearance or watching them move. However, as is shown in these images, vision systems might fail to figure out some of the physical properties such as mass and center of mass. Also, to watch the movement of the object, a specifically designed platform is required. The main contribution of our work is that the robot explores the physical features from the tactile feedbacks, which contains rich contact information, and the exploration process is simple and time efficient. We designed this challenge by using a set of template objects. As is shown in this video, we could easily change the configuration of the object in mass, center of mass, moment of inertia, and the friction of the handle. Here we demonstrate the importance of estimating the physical feature before starting the swing up. We let the robot arm conduct the same control policy while we change the center of mass of the object. As we can see, the objects are swung up to different poses. Similar result also happened when we changed the friction of the handle. As a data-driven method, we built a recycling system to repeatedly reset the object to the same position so that the object could start another trial without human participation. We collected 1,700 data with 33 objects by randomly select the swing-up action. We designed two types of tactile exploration actions, tilting and shaking. The tilting action will hold the object firmly and rotate the object in 20 and 45-degree poses. The bottom figures are the corresponding GelSight feedback in these two angles. The shaking action will loosen the gripper a little bit and keep the end effector moving forward and backward. The bottom video is a recorded sequence of the GelSight feedbacks. Here we showcase the GelSight feedback with objects of different physical properties. When tilting, different force and torque distribution generated by the object weight can be observed. When shaking, different friction and vibrations can be observed from temporal sequences of the tactile signal. Here we introduce our whole pipeline. The robot first conducts tilting and uses CNN networks to process the GelSight signal into a one-dimensional feature embedding. On the other hand, the shaking signal are processed by a RNN network into another embedding. Then the embeddings are concatenated and fused by a fusion model, which outputs a physical feature embedding of the object. After that, a forwarding model will take the physical embedding and control parameters as input and predict the final swing-up angle. During training, the whole pipeline is trained in an end-to-end manner. During testing, a set of control parameters will sampled, and the one with the predicted angle most close to the desired pose will be selected as the action to take. Here is our experiment result. We compared our method with random action and variation with no GelSight inputs. Our method significantly outperforms the baselines, which confirms that our tactile exploration indeed learns the physical feature of the object. We also did an ablation study by comparing our approach with tilting only or shaking only variations. As we can see, the idea of fusing multiple exploration improves the final performance. The forward model can further be used for control. We sample different actions and choose the optimal action to reach the goal. Here the goal is to swing up to 90 degrees. The robot successfully swings objects with different physical properties into the desired angle. All the objects here are unseen objects, which is not included in the training set. It can also generalize to different goal angles. Here the goal is 180 degrees. We also use a three-layer MLP as a disentangled network, which takes the physical feature embedding as input and regress to the numerical value of mass, center of mass, and moment of inertia. Another branch of the network outputs a classification result for the friction. From this table, all the model variants outperform the random baseline, which proves that all the physical properties are included in the learning embedding. In addition, we can observe from the result the difference in focus between each of the exploration actions. For instance, the tilting action is good at reasoning the mass and center of mass, which outperforms the shaking for 8% in mass and 4% in center of mass on the unseen situation. This is mainly because the tilting action provides stable torque force signal by placing the held object at different angles, for which it's easier to calculate these properties compared to shaking. On the other hand, the shaking actions achieved 93.9% friction classification success rate, which is higher than tilting action by 15%. This is to the fact that, different from tilting when the object is held firmly, shaking loses the gripper to enable enhanced sliding of the object, capturing friction information. Another advantage of learning joint physical features compared to estimating each property individually is its potential to generate task-oriented feature embeddings, where the objects close to each other in the embedding space can share similar control policies. We use PCA to project the learned physical embedding from combined method to points on the 2D plot, and visualize all the testing results of the 6 unseen testing objects in the left figure. We also visualize the data distribution of these test samples in the right figure, where the x-axis refers to the control parameter and the y-axis is the final swing-up angle. As we can see, for objects with similar policy distribution, for example like object 5 and 6, the distance between their embedding is also short. And for objects with large difference in the policy distribution, for example like object 1 and 4, the distance between their embedding is also large. This result confirms that the learned physical embedding are indeed task-oriented, which largely benefits the dynamic swing-up manipulation. In summary, the main contribution of our work includes an in-hand tactile exploration for gathering observations of object physical properties, a learning-based forward dynamic model based on fused tactile exploration data with self-supervision. Thanks for watching.